Draft physics video presentation. Alright, so I thought I would link to a couple of videos I did yesterday that really on a unrelated subject, partly a little bit on Tesla and the, I don't know, truth value of crap, we'll say, and just how bad it is, really. I mean, people just keep defending bullshit. So anyway, I did a video on this guy called Superhuman Dance, and he did a response video, an hour plus, where he responded to about 2 minutes of my video. Really didn't respond to any of the substance of the content. Anyway, so I just thought I would link to them because, you know, I don't really have a channel. Can't use philosophy, kind of, I don't know what you want to call it, commentary, opinion, something. I don't know. You have to be so careful about what you say about anything, because YouTube will censor you and abolish your channel. So the Amendment channel is currently suspended. It has a strike, and you know, for videos, you know, it's 2 strikes technically. For, you know, videos I published years ago, you know, and I'm supposed to go through my thousands of videos and figure out which one offended somebody. Apparently that's their policy. Anyway, just nonsense. So anyway, just saying, I did make a couple of these videos for which I can't really promote them any other way than to mention that the website, you know, you can't subscribe to it. You know, I suppose I could make such a feature, but I wouldn't because it seems kind of evil to me anyway. But anyway, just so I pointed out, it has a little bit of physics in it. So that's it. So yeah, link below to the Do Not God website. Anyway, and such. So back to the normal physics. Yeah. So I guess I'll preface again, start with a drawing of some kind, pointing out what the subject really is of this distinction between these different forms of scattering and what's happening with the photons, and provide the counter argument. Sorry. Oh, that's a little bit further over than it needs to be. Okay, I'll fix it here. Oh, that was way over there. Whew, who broke it? Anyway. Okay. Yeah. So the idea is that you can have scatter in different ways for this thing that's called a photon. And again, I don't see any rational way to describe a photon except to point out that it's energy. Okay. At a frequency. All right. And the energy has a thickness, width that's proportional to the frequency, although I'm not drawing it that way. That's what it is. It's proportional. It's the frequency and the polarization is what they call this, but it's kind of it's really not the best kind of term. There should be some other word for the volume of a photon. But anyway, so it's going to interact with different objects of different sizes, and the real point is most of these objects in the small physics world are going to be smaller than the wavelength, and so there's rules for what happens when you're interacting with something really small, like just an electron, versus an atom, versus a collection of atoms, and the rules will end up being different because obviously you're going to start affecting photons as complete things versus photons as individual little bits of quanta. And there's also going to be the difference in the terms of you're going to be affecting many things instead of just a single thing. So the real argument to be made is that the scatter, a fundamental distinction, just as it's fundamental to understand the photon has to interact with these little tiny electrons fundamentally. In the most fundamental scale, it's the electrons and the photons that have the keenest interaction. But it's also important to understand this idea that scatter happens as a group function. So you don't shoot light through one little molecule of atmosphere with one photon. We don't do that experiment, and that experiment won't create anything you can see. And the truth is what's going to happen in scatter is that there's a bunch of things of a size getting close to even the size of the polarization. So you have a bunch of stuff floating around in the atmosphere. The photons are going to interact in the sense that they're going to go through some of these bits, and it'll take time, so they'll use up time, which is going to ruin their phase. So as we've gone over this before, but the phase is critical to a photon being receivable, is that the little bits have to be in the right order. And so if I change the order, if I change the phase of one bit of the photon and move it to a new location, I've changed its frequency, and therefore it can't be received. If it has two frequencies in it, you know, an A and a B, it's not one frequency, it can't be received as a photon. It has to have a consistent frequency for a durable amount of time. So scattering, the me scattering, is with these little bit bigger objects, and they're essentially going to create slits. You know, they're going to create areas between them. Okay, they're going to be different openings for reflections to go through. They'll bounce off of each other, the pieces. They'll reflect internally inside. And what's going to come, what's going to be the byproduct of the chaos of all these little bits hitting different pieces. This bit will hit this piece, this bit will hit this piece, you know, this bit will hit some other piece, is that a bunch of photons will do that. It'll be group behavior, and in the end you're going to get reflections, and you're going to get lots of points where there's a constructive meeting of those bits, the photons, the elements of the photon. So a bit bounces from here and a bit bounces from here, and they end up hitting some location where your eye is going to be, and at that location the bits are combining to create a photon at the right frequency. So you're just remaking something the system broke, the chaos of the massive amount of atoms and a massive amount of photons will mix together and create pieces of energy that will reconstruct what went in. So what went in was pretty consistent. It's going to get broken to a bunch of pieces, and you're going to get pieces back out. And clearly there's going to be angles that you would look at where the phase coming out will be broken. Okay, it won't have the frequency necessary to be seen in locations where you're going to see it. So it's not constructive and destructive. It's just that there'll be places where you're back on phase. That is, there's a 360 degree change in the bits coming from this place, and so they're back in alignment. They're not too close to each other. They're not. It hasn't broken. The frequency is remade, and the phase if it's a 350. I mean, we've already been over this, but if it's a 360 degree phase shift, it just essentially means that the bits are still in the same alignment. There's just a change in the order. You know, a 1 is lined up with a 2 now, but that doesn't matter. As long as they're aligned, it'll be counted as a photon. Yeah, so I sort of went over this before, but that's all. The one form of scattering, you're talking about what happens to almost talking about interactions with smaller pieces of space. You could say it that way, in the sense that the many photons come in, a few bits come out, and that's the kind of scatter you're getting. And in the other example, you're going into a big field of bits and essentially just doing a bunch of experiments where you're going to end up with the diffraction of the photons, and there'll be places where the diffraction constructively rebuilds a photon and places that it won't, and that's it. So it's like the dirty piece of glass in the interferometer being the simple mechanism to create the Newton's rings, the pattern created in interferometers. And it's basically the same mechanism in the sense when you have a whole bunch of scattering objects, they will end up creating essentially a bunch of diffraction and a bunch of broken photons. And if you have enough broken photons and the pieces are all going in similar directions, you'll have what will decide whether you put the pieces back together is whether or not the phases are right. So if you can rebuild the phase, you can rebuild the photons. If you can't rebuild the phase, then you won't have any photons. And that's it. Alright, so we'll play this and such.
Welcome to Lecture Online, and here taking a closer look at Mie scattering. There's one more aspect that we should talk about. And so again, coming back to the relative size of the particles off of which light will scatter. So these are the photons coming from the sun, entering the atmosphere, and scattering out the very small particles like atoms and molecules in the atmosphere. The radius of the...
It's probably a pretty poor example because he has the light coming in horizontally and then showing less scatter going to the sides. And for ultraviolet light, there's more scatter going perpendicular. So I don't know if that's very consistent. Professor Lewin said, you know, the 9 times, he says the rate at which ultraviolet light scatters is 9 times that of infrared light. Professor Lewin says it's 6 times. So, you know, I'd say the 6th number is probably the right one.
Those are about 10 to the minus 4 micrometers, which would put it at about 100 nanometer. No, not 100 nanometers, 100 picometers. So less than a nanometer, so less, about a tenth of a nanometer, so to speak. And because of that, particles being very small in the atmosphere, we have what we call Rayleigh scattering. So the scattering kind of looks like a peanut, where we have the predominant scattering in the direction of the incoming light, forward and backwards, and there's some relatively small amount of scattering towards the sides.
So again, that doesn't make much sense with the whole argument that the ultraviolet light, the blue light, is being scattered out 6 times the rate of the infrared light in a perpendicular direction. So I don't know, but whatever.
When the particle gets larger, for example, when the radius of the particle gets to be about 0.1 micrometer, which is about 100 nanometers, about the size of a UV photon, then you can see that the scattering becomes more directional. So then we call it Mie scattering. And so the predominant amount of light gets scattered forward in the forward direction, the same direction as the incoming photon, and less light gets scattered to the sides and backwards.
And I would argue that that's always true, and it all just depends on what you're calling the difference between the light being transmitted and the light bouncing off. And so it all depends on what you're counting as scatter versus transmission. So you're transmitting more in light in the forward direction, and if you call that scatter, well, yeah, more of it's going to go forward.
And then you can see as the particle gets very large, here a particle in the range of about 1 micrometer, which is larger than the wavelength of visible light. Visible light is from 400 to 700 nanometers, which is 0.4 to 0.7 micrometers. So when the particles become larger than the wavelengths of the photons coming in, then we have a very pronounced what we call Mie scattering. It ranges to the border of optical scattering. And then you can also see that there tends to be what we call an interference pattern, that diffraction pattern that then evolves.
So there are 2 different things. The diffraction, that is the spreading, is one thing. The fact that you only see light in certain locations is the other thing. And again, it's not being caused by interference, it's just being caused by you either put the phase, you either get the bits back on phase or you don't. If you don't get them back on phase, you can't put them back together. If you get them back on phase, you have the possibility of putting them back together. If you have enough pieces, you can make a new photon. So all it's really saying is that you can put the photons back together after they've interacted with things from different distances, you know, if your phase is correct, if the distances are commensurate to a wavelength of the light, then you can put it back together. Anything else isn't going to work.
You can then see that the scattering, the magnitude or the intensity of the scattering, then develops these lobes. So we have strong scattering in this direction and very little scattering in this direction, and strong.
So again, it does scatter in the other directions. There's broken photons moving in those directions. You're just not putting them back together, so you won't see them as a photon because the phase is broken. And that's all there is. So there's energy going smoothly in all directions. The diffraction spreads evenly. And all you're really saying is through the process of that diffraction, there's some angles that reconstruct a photon because it puts them back on phase, and there's some that don't. And if they're not on phase, the frequency's broken.
Low, strong, so forth. So we have the separation of regions in different directions where you have strong scattering and low scattering, strong scattering and low scattering. And these are the typical patterns that we detect when we do, of course, radar waves. With radar waves, we have these what we call side lobes and predominantly scattered lobes like that, where we have lobes coming straight back on the incoming radiation. And then we have regions where there's very little scattering back. And then we have these side lobes here that people have to contend with when they're trying to...
So that just has to do with the size of the structure. So like the stealth bomber, it creates a bunch of surfaces that are of a certain size to confuse any radar. So just making it different sizes means that you'll create, if different sizes to the objects means that the radar that gets reflected back is automatically sort of going to be off phase because the object sizes are different, and so it's breaking the photons into pieces that aren't consistent, different size pieces. And the real thing you're trying to avoid is to ever send back whole photons, to have a surface that's smooth enough or flat enough to be bigger than the wavelength of the photon. So if you have a surface that's larger than the wavelength of the photon, then that's going to be a more visible surface because there's not going to be any problem with phase. You're not going to break the phase. So first you need to break the photons to fool the radar. And then you need to break them in such a way, angularly, that there's little probability that two broken photons can get back to the same location. So if you make sure your reflections are all in different directions, you'll be it's more likely you won't be sending back any reconstructed photons.
Understand what's going on when they send radio waves to a target, and the target then scatters in the same sense as what we call mean scattering. And then we have these directional lobes of scattering. Again, that happens at particle sizes that are larger than the incoming photons. And we'll give you a little bit more idea of how that really works. So don't imagine that the scattering is the same in all.
So this radar is rather large. You're talking about wavelengths that get into, sizable chunks and such.
Directions, or that it's uniform in all directions, but there's actually what we call a interference pattern that develops because of the scattered waves then beginning to interfere with each other, and you have these what we call interference patterns.
So again, there is no interference. He doesn't explain the interference, doesn't explain how any of that would possibly be a manifestation of hitting something with these energy. How does the energy get how does this object getting hit by the photon decide which lobe it's going to send the light in? So again, there's no decision, and clearly the photons aren't, big wobbly atmosphere and all this other stuff that's going on. It's not the photons interacting with each other and interfering with each other and destroying each other or doing any of this stuff. The photons can't do any of that. It's just a matter of you're either going to put the photons back together or you're not. Surfaces break the photons, small surfaces especially. They break them, and all you do is either remake them or you don't remake them, and that'll be decided by phase. If you can put them back on phase, then you can remake them. So that's the simple argument, the simple explanation. It fits all the data. There is no wave interference. There's just breaking and then remaking. Simple enough argument, made over and over again.
When they're out of phase, when they get scattered off the particles. So that's additional information to understand how photons work. And now in the next video, we'll get the details of how that relationship happens between the scattering coefficient and the various ratios of the particle size to the wavelength in the scattering.
Yes, well, we'll see. Anyway, so I guess I'll call that a video. Short and whatever. So some other subjects it's probably worth making some other videos on, such. Yeah, I want to just play these out. Since I started, I want to finish them, so I'm going to finish them. In fairness and such. So sorry if it's getting redundant and boring, but photons are interesting. Until next time, such.